Sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
Okay, and you're able to see the slide.
Yes, sir.
Yes, sir.
Yes, sir.
Very good. Good. If you have any questions, or if I'm going too fast, or if it's not
Yes, sir.
audible, so please shout. Okay.
Fine, sir.
Yes, sir.
Okay. Anyway, so we are going to, right at the first time of the lecture, first day of the lecture, I had told that we are going to cover 4 topics in your course. That is seismic, that is gravity, then magnetics, and then we have the seismic refraction, which you're going to start covering today, and then we have the seismic reflection. Out of these 4, the gravity and magnetics, are the ones which are hardly used. They are used, but in terms of maximum use, it is the seismic. And in the seismic, the maximum use is seismic reflection, the next topic which we'll cover. So the seismic refraction is used for a specific purpose for the hydrocarbon exploration, which we are going to talk about. Okay. So you have studied in the light in the school, 11th or 12th standard, you have studied about seismic refraction in light. Am I right?
Yes, sir.
Yeah. So how did refraction take place? How does light refraction takes place? When light goes from one medium to another medium, there is a refraction, right? Or bending of lights.
Yes, sir.
So why does it take place?
Because of
Why?
the density difference.
Is it because of the density? What is the term called? What is the term called? Density is not the answer. There is a term which is called. It may be related to density, but there is a specific term which is like when light goes from denser to a rarer medium, it will bend towards the normal or away from the normal. Or the light goes from the denser to rarer to the denser, it will bend to the normal, towards the normal or away from the normal, right? That is, if it goes from air to water or water to air. That's what the example I gave. Or air to glass and glass to air. So, but what is it called? Why does it take
Change
place?
of medium.
Yeah, change of medium, but why? That's correct, 110%. It's because of the refractive index. You had done some problems when you were in 10th standard. You did problems what is called as RI, refractive index. Okay, the refractive index is different for glass, is different for water, is different for air. Yeah, it's related to the density, but it's not the same. So because of the change in the refractive index, there is the refraction of the light, right? So it's the same thing we are going to do over here. Now what did this? Restart, postpone. It says restart now. Restart your computer to finish installing. Oh no, postpone. Okay. So we are going to study about the seismic refraction now, and we will see how it goes. Okay. Remember, in light there are 2 things, refraction and reflection. So we are now going to study about refraction. Okay, when light goes from one medium to another medium, there is a bending depending upon whether it's from a rarer to a denser or from a denser to a rarer. It's the same principle you're going to apply now. So the first thing we're going to talk about are the seismic waves. So as I mentioned in your first lecture and partly yesterday, that whenever you make impact, that means suppose you stamp your feet on the ground, you're going to generate seismic waves. Now the seismic waves that you generate has both body waves and surface waves. Okay, so let's see about the body waves. Can you read the text given? Okay, it says
Yeah.
the body waves are elastic waves that propagate through the Earth's interior. In reflection and refraction prospecting, body waves are the source of information used to image the Earth's interior. So we're going to use the same thing. We are going to image the Earth's interior using the body waves, the seismic body waves. Like the ripples on the surface of a pond, okay, body waves propagate away from the source and in all directions. Just like if you throw a stone in a pond, what do you see? You see waves going from the disturbance point towards the end of the lake or to ends of the sea or end of the river, whatever it is, right? If the speed at which body waves propagate through the Earth's interior is constant, okay, so let's say the speed at which this wave is propagating in the water is constant, and normally in water we say the speed of P waves or body waves is 1500 meters per second. Then at any time, these waves form a sphere around the surface whose radius is dependent on the time elapsed since the source generated the waves. So you can see on the red is the point where this disturbance has been generated, and you have the spheres, and it's given, time is given 75 milliseconds, 150 milliseconds, 225 milliseconds, and since it's water, the velocity is 1500 meters per second, and the depth is given. And you can see these are half circle. You are not going to see the full circle, but in true reality is full circle. Why? Because the medium is homogeneous and isotropic. It has a velocity of 1500 meters per second. So that is the picture which is given. So 1 millisecond equals 1,000 of a second. So what is, we are always now, you remember when we talked about gravity, we talked about milligauss. When we talked about magnetics, we talked about gammas, and we talked about nanoteslas, the units that we geophysicists use. So in seismic, we normally are using milliseconds or microseconds. So normally milliseconds. So 1 millisecond is 1,000 of a second. Is that clear so far?
Yes, sir.
Yes, sir.
So don't worry so much. The P waves are called primary waves, okay, because they propagate through the medium faster than any other type. So P waves are called the primary, sometimes called the compressional, because it travels the fastest. In P waves, particles constituting the medium are displaced in the same direction that the wave propagates. So that means how does anything moves, just like we talked about the conduction of heat. If you're heating one end of the rod, you get the other end of the after some time the other end of the rod gets heated up, right? You know that. And why does it get heated up? Because the one end which is you're heating up, the molecules vibrate and they transmit the heat from one to another, and finally it goes to the other end. So it's the same thing. In P waves, particles constituting the medium are displaced in the same direction that the waves propagate. We'll see a diagrams very soon. In the case, the radial direction. Thus, material is being extended and compressed as P wave propagates through the mediums. So you have like a piano accordion or something. You blow in and you blow out, and you blow in and you blow out. So that is, you compress and you rarefied, you compress, you rarefied. So that is exactly how the wave moves from one end to the other. And then we have the S waves. The S waves are sometimes called the secondary wave because they propagate through the medium slower than P waves. So they propagate slower than P waves. Okay. In S waves, particles constituting the medium are displaced in a direction that is perpendicular to that of the waves is propagating. So we'll see a diagram in very soon. Okay. Now, for the purpose of your course, we are mainly going to concentrate on body waves, and that too only on P waves. We are not going to much cover about S waves, but if as a geophysicist tomorrow you get a job, you are always going to study both P wave and S wave, because S waves and P waves combined gives a lot of information of the subsurface of the earth that we are interested in, and that P waves doesn't give alone. Okay, but for the purpose of your course, we are going to concentrate only on P waves, or the primary waves, or the compressional waves. So these surface waves, you can see again the point red is the disturbance point, and then you can see what's happening at 75 millisecond time elapsed, 150 millisecond, 225 milliseconds, and 300 milliseconds in water, which is 1500 meters per second. So you have a water which is 1500 meters per second, and the surface waves are propagating in that. Okay. So surface waves are waves that propagate along the Earth's surface. So normally, if you are a seismologist, you are mainly interested in the surface waves, because the surface waves travel very close to the surface and the amplitude is maximum. And as you go down the surface of the Earth, the amplitude decreases. So obviously, the destruction of the wave decreases. So their amplitude at the surface of the wave can be very large, but the amplitude decays exponentially with depth. You don't have to worry much about the so these are the surface waves. We are not going to talk much about the surface waves. The reason being, surface waves are important to the seismologist or the earthquake people because it causes the maximum destruction, and is because it travels close to the surface of the earth and it has got the maximum amplitude. We are going to concentrate on body waves, and we are going to concentrate on the P wave part of the body wave. Okay, so this is the Rayleigh wave, a part of surface wave. You can see on the top diagram. So on the top, you can see that it's the Rayleigh wave, and as is moving circular in this thing, it's got a big amplitude, and as it's going down the depth, it's decreasing, and you can see within 0.8 of the wavelength, it has decreased. So it decreases very fast. So the maximum damage is caused on the surface of the earth. Now, somebody of you may say, if this is not of our interest in size and it is of interest to the earthquake people, as why are we bothered about the surface? Yes, we are bothered about the surface waves because this is noise to us. We have to get, anytime you are generating any wave, it generates both surface waves and body waves. You cannot stop from creating surface waves, but we have to control the surface waves. How do we control it? So we have to get rid of the noise, and we have to enhance the signal. So that's why you need to know about the surface waves. Okay. So this is the the energy decreases by 1 by r squared. That is with the distance. You don't have to worry much about that. Now let us go to the elastic property. This is important. So it says that propagation of seismic waves in earthen media is controlled by the elastic properties of the medium. Okay. Now what did we say in gravity? We said the physical property of interest in gravity is what? What is the physical property of interest in gravity exploration? All of you forgot.
Lateral change in density.
Very good. Lateral change. And what is the physical property in magnetic exploration?
Lateral change in magnetic susceptibility.
Excellent. Who is that? Who is that?
Harshal.
Excellent. So what is the property in seismic refraction? The physical property. The physical property in refraction, seismic in earthen medium is controlled by the elastic properties of the media. You remember, it is the elastic properties of the media. Like, you could have a shale and you could have let's say a basalt. A basalt will show very high seismic velocities, maybe 4,500, 5,000 meters per second. A shale may show 200 meters per second or so. But the density of shale obviously is much less than the density of basalt. It is not controlled by the density. It is controlled by the elastic properties of the media. That is the answer. The elastic properties of the media is the physical property. It is not the density. So don't say that it is the density. Just like you had said that, remind me, postpone. Okay. Just like you said, we said that the refractive index is important in seismic, in light in refraction. It is not the density, right? So it is the elastic property of the medium is the physical property. Okay. Now in this case, it is not only lateral. It could be vertical. It could be lateral. Unlike gravity and magnetics, it is only lateral. Okay. We'll see that. So other media are considered elastic to simplify treatment. Otherwise, there'll be too many elastic constants. So for the purpose of your study, we assume that the Earth is homogeneous and isotropic. So homogeneous means it is the same in all three directions, X, Y, and Z. That means the depth. And isotropic means it is the same in all directions. Okay. And we'll see if there is an explanation of homogeneous and isotropic. If it is not, then I will try to explain to you. But for the purpose of we have to assume the Earth is homogeneous and isotropic. So the number of elastic constant decreases from something of 27 to about 3. If you were a geophysics like me, you would consider the Earth as not inhomogeneous and anisotropic, and you will work with the wave equation with 27 elastic constant. But that's not the purpose. For our purpose, we consider it homogeneous and isotropic. You have learned when you were in school, you have learned about homogeneous solutions. Didn't you hear about that? Homogeneous solutions, heterogeneous solutions. You've read about that or not?
Yes, sir.
Yeah. For example, if you mix salt and you mix sugar and both are white, and let's say the grain size also same, then how will you know it's homogeneous or heterogeneous? It's very difficult for you to find out because both are white, okay, in a dry form. Very difficult, right? So homogeneous is something like uniformly mixed. But if you put it in liquid, okay, then what is happening? You go on adding salt or go on adding sugar till one settles under, and then you say that it is no longer homogeneous. You have done those. You have read about all that. Isotropy deals with distance. That means it deals with directions, just like the difference between speed and velocity. You have speed, which is scalar, and you have velocity, which is vector, right? So we normally refer to speed as the scalar quantity and the velocity as the vector quantity. Okay, so similarly, homogeneous is something, it's just like a grab solution, it's homogeneous. Isotropy is very much with the directions. Okay, we'll see if there is a slide. If not, we'll see later on. Elasticity, but for the time being, you have to, we have considered the Earth as homogeneous and isotropic. Elasticity of the material studied by using the concept of stress and strain. So how do you know the elasticity of a medium? You have studied that in your 11th standard or 12th standard, and you know that if you have a stress versus strain curve, okay, and then if the stress is proportional to strain, then we say it's elastic. If it is not, just like you are seeing in the diagram, the elastic limit, then it goes to the plastic yield and finally it ruptures, just like earthquake. So, you know, if there is a fault, there's a stress building up with a period of time. Ultimately, when the rock is not able to hold the stress, it releases the stress along the fault and it ruptures. Okay, so the stress is proportional to the strain is within the elastic limit. So we have to consider that we are within the elastic limit of a homogeneous and isotropic medium. Assume that the displacements are small. You know, the displacement should be very small. Okay, that means the displacement of anything with a particle. So Hooke's law holds for most of the rocks if the strain and stress are not very large. If there is a very large stress and strain, then there is a problem. So normally, you know, the Hooke's law will work for very less strain, 10 to the power minus 4, 10 to the power minus 5 strain. So it works for very low strain. Okay, so again, this is a big field. We are not going to go in depth into it. If you ask what happens if the strain is large, yes, we need to study at large strain, and that's what the civil engineers do. How they do is another problem. So as far as geophysics is concerned, whenever there is a seismic wave travel, the strain is very small, or the order of 10 to the power minus 5 or 10 to the power minus 6. Okay, so you have to remember, and stress is proportional to strain in this homogeneous and isotropic liquid. So we said that because we assumed the medium as homogeneous and isotropic, so we are going to get the number of elastic constants are less. And we said, let's say in this case we have 3. So we have Young's modulus, we have bulk modulus, and we have the rigidity or shear modulus, which is given. And the definition is given at the bottom along with it. But on the top, you say elastic constants are defined as the ratio of different stresses. So if you have a tension, or you can have a compression, so you can, you know, like you can pull something like an elastic band. You can pull it, its tension. If you release it, it gets compressed. Okay, you can apply a pressure. Pressure means whenever you apply the pressure, it's uniform on the all sides. Or you can do a shear. Shear means like cutting. So you can, if you rub your hands, it gets heated up. It's like shearing activity. So these are these 3 things, these define the elastic constant. So we have the Young's modulus, we have the longitudinal stress by the longitudinal strain, we have the bulk modulus, which is volumetric stress by volumetric strain, and we have the rigidity or shear modulus, which is the shear stress divided by the shear strain. So remember, any of these modulus, it is stress by strain. I explained to you already before, the Hooke's law. So stress, it's only the different type of stress. So Young's modulus could be longitudinal stress or could be a compressional stress divided by compressional strain. Bulk modulus always has to be volumetric stress by volumetric strain, and shear modulus is shear stress by shear strain. So we'll see the diagrams. Okay. Now you look at this Young's modulus. It is a measure of stress-strain ratio for a simple tension or compression. So you can see if you pull, it was length L. Let's say it's a rubber band. It's a length L, and if you pull it, so it becomes L plus delta L, right? It stretches. So what is the stretch part? It is delta L. What is the force? The stress. Stress is nothing but pressure. Remember. So pressure is defined as force per unit area. You know that, right? Pressure is force per unit area. So stress is pressure. So stress is force per unit area, F divided by A. And at the bottom is the strain. So on the top you have the stress, and at the bottom you have the strain. So what is the strain? It is the change, which is delta L divided by the original. So it is L. So you have stress by strain. In this case, Young's modulus is F divided by A divided by delta L by L. So the units are, if it's in FPS or units, so it is dynes per square centimeter. If it is in CGS units, or in MKS unit, it will be newtons per meter square. Okay. The greater the value of E for a solid, so the greater the value of E for a solid, the lesser will be the deformation for the applied tensile or compressive stress. So if we have basalt or if we have granite, okay, the value of E is very high. So that means the deformation, it will be very small. If you have a shale or if you have a slate, okay, then the E value is less. So obviously the deformation will be more. Is this clear? Is this diagram clear? Because these are things that you have done when you were in 11th or 12th standard. Is there any question on this? It's clear, huh? Okay. So
Yes,
yeah. So what are the typical Young's modulus of the rock? You can see basalt. It has a value of 2.8 to 7.96 or whatever it is. Avoid the thing that is written in the red, because these are the values that I got from all the areas that I surveyed, and I made a summary of it. But you can see the range. The range is 9 to 10 into 10 to the power 5 kg per centimeter square. Okay, so the basalt or granite are very, very high. Okay, sandstone, you can see sandstone relatively is less, 0.5 to 5. Okay, so these are the different Young's modulus of the rock, and I told you the larger the E value, the greater is the strength of the rock, the less is the deformation, like basalt or granite. Unlike sandstone, which is 0.5, so obviously it has got less stress strain. Okay. Okay, at the bottom it is written for most rock, whatever it is. You don't have to worry about. Now, some of you will say, sir, we are not interested in basalt, granite, maybe quartzite. Why you're not interested in basalt, granite, and quartzite? It's not of interest to you. Why?
Because we can't find hydrocarbons in it.
So hydrocarbons, so what? Yes, you're a hydrocarbon person. So
we will only look into the rocks which contain hydrocarbons, which are sandstone or limestone.
you are close to the answer, but you're not on the answer. Who is this?
Sumed.
Sumed, you are close on the answer, but you're not on the answer. Because in hydrocarbons, you're always going to deal with sedimentary rocks. You're not interested in igneous or metamorphic rocks like which have basalt or granite or quartzite, right? You are interested in sedimentary rocks.
Yes.
So that is the answer. So your answer is you're not interested in those, but you are interested in sediment. Now let's say somebody comes to you and tells you, we are interested in doing a magnetic survey, so we are interested in area where there is basalt or granite. Why? He's a hydrocarbon person. So now he is exploring in an area, and he says, my area of exploration, I'm going to use the magnetic because this area has basalt or granite. Why?
To find depth, sir.
Depth for what?
Depth for hydrocarbons, because
Hmm. Yes, what depth? Depth, we are always interested in depth. What exactly? Why we are using a magnetics in an area where there is basalt or granite? Why? For a hydrocarbon? Why? That is the question. Remember, I told you magnetics. I never told you gravity. What is the answer for that? I had explained to you with diagrams, if you recollect, but you forgot. Because we are interested in the thickness of the sediments, and the magnetics give me the depth of the basement. The basement rock is the basalt or the granite. It's like a basin. The bottom of the basin is the granite or the basalt rock. The basin is filled with sediment. So if I want to know the thickness of sediments, which is of my interest because I'm a hydrocarbon person, so I need to do the gravity on magnetics because I need to know the thickness of the sediments if I can map the basalt or the granite. Didn't I tell you that? I had told you that. Isn't it? So don't.
yes, sir.
Yeah, so remember it, because if you say that, we are not interested in basalt or granite because we are hydrocarbon, you make your point, answer very clearly. In seismic, we are not interested in basalt or granite. If it is a gravity or especially if it's magnetic, we may be interested because we want to find out the thickness of the sediments. Okay? Okay. So we can go to the next one is the bulk modulus. So the bulk modulus, you can see the diagram. It says you had a large cube, and in that cube you compressed the cube. You can see the pressure is applied from all the directions, and the cube has got compressed into the large cube. So what's happening? It is a measure of stress to the strain ratio for hydrostatic pressure P that produces a change in volume. So there is a change in volume. You remember the volume has X, Y, Z. So the volume has changed from the original to something which is in the dashed part. So again, K, which is the bulk modulus, again is the stress. So force by unit area is the stress divided. In the last case, you took delta L by L. In this case, delta V by V. So it is the volume. Okay, so there is a volume change. It is not the compression or the longitude. It's not stretching or compressing. It's the volume change. So give me an example of a volume change. The reciprocal of bulk modulus is called the compressibility. Okay. So how much I can compress is a function of the K value. So 1 by K is the compressibility. So give me an idea of the compressibility or the bulk modulus. In your, in your normal life. If you open your eyes, you know about it. What is an example of the compressibility? You have heard the word compressible, right?
Yes, sir.
So where is it applied? If you said yes, where is it applied? Compressibility is very normally applied to what?
So LPG.
Yeah. So what happens in LPG? Very good. What happens in LPG?
So the gas is compressed into a cylinder.
Yeah.
It is then, because of the pressure, it gets converted into liquid inside the cylinder.
Yeah, liquid is something that we can avoid. So what is happening is, in that cylinder, they have put the gas under pressure. So when you open it, the gas comes out. Same thing if you're having a motorcycle, the chap fills the air from the tank. He puts the air in the tank, and when he puts the nozzle with pressure, it goes into your tire, right? So how much air or how much gas can be put into a cylinder is a function of how much we can compress. It's a function of the compressibility. Is that clear to you? So it's a example of volume. So volume means it is acting in all directions. And then finally we come to the last elastic modulus, which is called rigidity or shear modulus. It is a measure of stress-strain ratio of a simple tangential shear strength. So you can look at the diagram on the left-hand side, and you can see shear modulus issue shear stress divided by shear strain. In this case, you can see what's going to happen. You apply the force, parallel to that hatched part, and what happens is it shears off. Shear means the word shear means tearing. The English word shear means tearing or cutting, whatever you can call it. So that's why the shearing it has come. Like if you have a pack of cards, you have playing cards, right? You have playing cards, and you put the deck of playing cards on the table, and you apply a force, parallel to the cards. What happens? The card slides one over another, right?
Yes, sir.
Yeah. So that is called the shear stress. So that is the shear stress. So that is the one which is showing in the diagram. So you have the mu, which is the shear stress, is again the force by area. In this case, it is the tangent of the angle theta, and the theta angle is defined there. Shear strain is the result of deformation without change of volume. It's given also as a pile of cards can be sheared. So there is no change in volume. You have to see there is no change in volume. It is only a change in shape. There is no change in volume. And shear modulus for most of the material is between 1/2 and 1/3 of the value of Young's modulus. So half or 1/3 of E, which is the Young's modulus. So we said Young's modulus was the highest. And then we came to the volume definition of K, which was the volume factor which is coming on, okay, which is called the bulk modulus. And then finally we came to the shear modulus. Now, why do you think the shear modulus is important to you? Give me an example. Where do you think the shear modulus is important to you? To the hydrocarbon people. Look at the diagram and you should be getting the hint of the answer. So what happens? Why are you quiet? You have to give the answer. So when you, for example, if you have a sandstone, right? Or you have a shale, and you have a hand specimen, those are sedimentary rocks. It's not slate. It's sandstone and shale, for example. So what do you see? If you have a hand specimen of a shale or a hand specimen of a sandstone, what do you see in that? And let's say it's, you have polished it. What do you see? That should be very quickly answered, no? What do you see in that?
So we can see small grains in sandstone.
No, I'm not worried about the grain. You look at the diagram. With respect to the diagram, you should be getting a hint. Of course, grain size and all are important, whether it is Arcos or anybody. So you will see layering. Don't you see layering? Whenever you have in a sandstone or a shale, you see fine layers. Don't you see that?
Yes, sir.
Yeah. So now if we apply a stress like F onto the sandstone or shale, so it will break very easily because it will slide along those boundary of the layers. It will slide. Those are the weak points. So it will slide along that. Is that clear? But that doesn't happen. That doesn't happen in the case of basalt or granite because they are, they are like mass. They don't have that layering property unlike sedimentary rocks, isn't it?
Yes, sir.
So that is why the rigidity modulus is very, very important in case of, if you can do a seismic survey and you can find the rigidity modulus at a depth of 8 kilometers, so you should be able to know, okay, this is a shale or a slate or whatever it is. So that's the important parameter. Okay. And then finally we come to the Poisson's ratio. It says it is a measure of the geometrical change in the shape of the elastic body. And you can see on the diagram on the left, on the right hand side, your right hand side, you can see the Poisson's ratio. So it says you see what's happening. The D is decreasing, delta D by D and delta L by L. So you can see the change in the so if I if we say elastic body and if I stretch it, what will happen? The L will also increase and the diameter will also decrease, right? So if you think D is the diameter, so change in diameter divided by the change in length is the Poisson's ratio in this particular case. So it's a measure of the geometrical change in the shape of the elastic. It is a change in the geometrical shape of the elastic body. Remember, when we did E value, we came delta L by L, but we never took this delta D by D. We took the force per unit area as the numerator, and the denominator was the same, delta L by del. But if you take this, normally if you stretch an elastic band, you will see that it will thin, so the diameter changes, the length increases, and this is what you get. So it is the Poisson's ratio is a very, very important parameter in seismics. You remember that. Cylinder of length L and diameter or whatever it is explained on the right hand side, subject to a compressional state. In either case, Poisson's ratio, which is a dimensionless quantity, is delta D by D divided by delta L by L. Now, Poisson's ratio is unlike the other three elastic constant, that is the shear, the K values or the E values, which is in dynes or newtons per meter square. In this case, it is dimensionless quantity, because on the top also you are having length, the bottom also you are having length, both gets cut, and so the Poisson's ratio, which is sigma, okay, is a dimensionless quantity, and the sigma is very, very important. Okay, let's see. Now you can see that sigma can never be greater than 0.5. You have to remember that sigma can never be greater than 0.5. For most hard rocks, its value is about 0.25. Value determined from dynamic method and is unstable. Now, what is the method? What you must be thinking, what is dynamic? The dynamic is the seismic. I told you seismic method works at very low strain level, right? 10 to the power minus 5 or 10 to the power minus 6. So they are called the dynamic method. If it is a static method where I can apply large stress and very small, very large strain, the displacement is very large, they are called static methods. Okay, so that is done by resonant column, and civil engineers do it. So the value that is not of our concern. So our concern is the dynamic, which is seismic. So value determined for dynamic method is unstable. For instance, if accuracy of velocity evaluation is 100 meters per second for two values, so you have, let's say, Vp is equal to the compressional wave velocity is 4,800 meters per second, and the shear wave velocity of that rock is 2,300 meters per second. Its Poisson's ratio is 0.35. But the moment you went down for 100 meters per second difference for 4,700 and then 2,500, you can see the Poisson's ratio has become 0.32. Okay, so this Poisson's ratio is very, very important. And why it is important? It gives you a lot of insight into the type of formations you are looking for. Okay, that's the whole objective. Sitting on the surface of the earth and you are going to send seismic wave, you should be able to calculate the Poisson's ratio. And of course, you'll see that Poisson's ratio also comes out from the shear wave velocity. So if you know the shear wave velocity, that is Vs, about which we are not going to talk in our exploration method. But if you can measure Vs, and if I can measure Vp, that is the compression and the shear wave, then I should be able to get the Poisson's ratio of the different layers that I encounter deep down within the earth. And that gives us a lot of information about the type of rock. So the Poisson's ratio is very, very important. You have to remember. And then you have to remember that sigma can never be greater than 0.5. So these are the elastic constant. You can define one with the other. So you have the shear modulus on the top, and you can define with respect to the bulk modulus and the Poisson's ratio. You can define the bulk modulus in terms of the Young's modulus and the Poisson's ratio, and the Young's modulus you can define in terms of the bulk modulus and the rigidity modulus, that means shear modulus. Okay, so only three of the four elastic constants are independent. Only three. All the four elastic constant can be expressed in terms of any two. What are the only three of the four means? E is independent elastic constant. We said that Young's modulus. We said mu, which is the shear modulus, and we said K is the bulk modulus. So these are the only three elastic constants which are independent for a homogeneous isotropic Earth. Others, all the four elastic constants can be expressed in terms of these three elastic constants, this and that. Is that clear to you? Okay, so this is very, very important. Okay, now is there any doubt on this? So we started off from the basics of P waves and S waves, surface waves, and we said that we are going to concentrate on P waves, and P waves has again two parts: the shear wave and the compressional wave. We'll only concentrate on the compressional wave insofar as your your curriculum is considered, or your study is considered, because we are not going to much talk about shear wave. But if you are working in the industry, you are going to work always with shear wave and P wave simultaneously, because it gives you a lot of insight into the different elastic properties or of the Mother Earth. Now, why seismic refraction? Now, just like we said that why seismic, why gravity and magnetics? We said we do gravity and magnetics to find out the thickness of sedimentary layer, right? For hydrocarbons. Didn't we say that? We do gravity to find out the thickness, or to find the presence of fault. We do magnetic survey to find out the thickness of sediments where the basement rock is magnetic. So what is the use of, why do seismic refraction? So seismic refraction is used for depth to bedrock or bedrock topography. So it is used to find the bedrock or the bedrock. Bedrock means hard rock. Okay, the bedrock or bedrock topography. We'll see the pictures in a minute. So information on rock condition, though obtainable from boreholes. Now this is applied for engineering because the seismic refraction is exhaustively used for engineering projects. So it is with respect to that is talking about information on rock condition, though obtainable from boreholes, is inadequate and could be misleading at times in complex site travels by faulting or buried channels. Okay. So with the help of data from a few boreholes, we don't have to worry about all that. This point 2 and point 3 is related to engineering. So resolution is better compared to natural potential. Now resolution means seismic is talking about seismic refraction resolution is better than gravity and magnetics. So gravity and magnetics are referred to as the potential fields. Okay, that is what it's talking about. So seismic refraction widely accepted for in situ investigation. Now I just now told you for engineering, geology and geotechnical problems, you don't worry about all these things. Okay. Now you look at the diagram. It says on the top you have a 1200 meters per second, a rock which is having a velocity of 1200 meters per second, and below it on the left hand side we have 3000 meters per second, and on the right hand side it becomes 4500 meters per second. So there is a lateral change in velocity of this basement rock. The rock below the red line at the bottom, the 3000 or 4000 is called the basement rock. There's a lateral change in the density, whereas there is no change in density, no change in the velocity on the top, and the depth is given 4 meters. And if you look at it very carefully, why there has been this lateral change in velocity of the basement rock, the rock below the red line, is because there is a fault. There's a step. You see the step? So there is a step, and there's perhaps some sort of faulting which has taken place. That's why we are seeing the change in velocity. So the seismic refraction is used to find the depth of the bedrock. It is used to measure the fault, the throw of the fault, where the fault has occurred, and so on and so forth. Okay. What seismic velocity can indicate? So what it's telling is just like gravity and magnetics, what we got, we took out a gravimeter, and we found out the gravity field in terms of milligal, and from there we tried to find out where exactly is the body. We did some exercise in that, if you recollect. If you have a magnetic, we see what is the lateral change in magnetic susceptibility, and from there we find out what is the thickness of the sedimentary rock, or if there's a buried object, we try to find that. So that is what the magnetics and gravity give. What does the seismic velocity gives us? So seismic velocity, if I measured, you remember the previous, I measured an area where I had 1200 meters per second, and I got a 3000 meters per second and a 4000 meters per second. Somebody asks you, what does this signify to me? Okay, can you explain to me? So that's what is answering. It says, it talks about the relative quality of the rock. So the rock which is having 3000 or 4000 meters per second is definitely much more competent or much more dense compared to the rock which is having 1200 meters per second. Maybe the bottom rock is, basalt, and the top rock is some sort of shale or whatever it is. So it talks about that. Okay. Then delineation of weak zone in a rock. So in this case, we showed it is varying from 3000 to 4000 meters per second. Why? There is a fault. Okay, so you can find the fault. The dynamic, I already told you, if you can measure all these velocities, that the densities, the K, and the seismic velocities, the VP and the VS and the density, then you can calculate the Young's modulus, the shear modulus, and the Poisson's ratio. And finally, the repairability of the earth material is important to the engineering people, because you must be saying, if you make tomorrow a lot of money and you want to buy a house, and let's say you want to buy a house on the foothill of at the bottom of on the foothill of a mountain or a hill. Okay, the contractor comes and he quotes, okay, so much of material I can scoop up, and the charges is this. And if it is it is very, very solid basalt, I need to blast, so the charges are different. So how repairable is it, or how not repairable is it, or you need blasting, you can talk about from the velocity. So for example, 1200 meters per second, you can go there and put a machine and you can scoop it up. But perhaps it will be very difficult for you to scoop up the rock which is having a velocity of 4500 meters per second. You need to blast it or fracture it, whatever you want to do. Okay, and that's what they do. You must have seen, they put the jackhammer and they make holes, and and they make big boulders, and they take it out. That is what they do. So we come to this body wave which we started off, and maybe this is a repeat slide or whatever, the slide not at the right place. And so we have the compressional, that is the wave, that is the primary or P wave we are going to always talk about. Shear wave, yes, it's a body wave, but we're not going to talk about much. But if you are a geophysicist, you're always going to work with both of them. Surface wave is not of interest to us in terms of exploration. It is of interest to us because we want to know how much of surface waves we generated, because it's noise, so we have to take control of it. Okay, how to reduce generation of surface waves, how to eliminate surface wave, so that we get more of a signal and less of a noise. So that is what it is. So this is the compressional. You can see on the right is direction of, I told you the direction of vibration is parallel to the direction of propagation. So you can see the wavelength, and if you can see the particles are widely spaced, then the particles come very close, then widely spaced, then they come close. So when they're widely spaced, they are rarefied. When they're closely spaced, they're compressed. So you have like a bellow, you compress and you expand, you compress and you expand, and the waves move. And which direction it moves? It moves in the direction of the compression or this thing. So that is what it's showing you on the diagram. You can see the direction of the wave. So propagation and contraction, P waves are easy to produce, and on the bottom it is giving you how the velocity of P waves. If I know the bulk modulus, and if I know the shear modulus, and I know the density, rho is the density in this case, then I should be able to calculate the compressional wave velocity, that is VP. That's what is talking about, the velocity of propagation. I think there's a better diagram. You come to the shear wave. So shear wave, you can see what's happening. In shear wave, we said direction of vibration is perpendicular to that of propagation. So this direction is the direction of propagation, but the particles are vibrating perpendicular to that. And you remember the perpendicular, if I'm moving along a direction, there could be two perpendicular direction. Okay, am I right? There could be two perpendicular direction or not, or there could be only one. If I have a line, like you're having the direction of wave propagation, there can be two direction of two perpendicular to it, only one perpendicular to it.
So two perpendiculars.
Very good. So we have two perpendicular. So one is called the one which is perpendicular to this, that is making up and down like this thing, that is called the shear wave, and the other is called the vertically polarized shear wave, VP, VS and VP. So here the bottom is again defined. How do you calculate the velocity of shear wave, or what the velocity of shear wave is a function of the rigidity modulus and the density, and or the velocity of shear wave, or the shear wave velocity is a function of the Young's modulus, the Poisson's ratio, and the density. So anytime you get the velocities of a rock down within the earth, you are going to talk about, or you're going to find out parameters of its rigidity modulus, the Young's modulus, and the Poisson's ratio, which speaks a lot about its properties. We are interested in the properties. Okay, that's the whole purpose. Okay, so now we go to the basic principles of. Is there any question so far? We talked a little bit of the different type of seismic wave, and we talked about the different elastic parameters and their importance in seismics. Is that clear, or is there any questions that you need to ask? You're free to ask. Or everything is clear?
Yes, sir.
Everything is clear? So you want to stop here, or we can go ahead? Are you tired, or what is it? You should stop here, or we can go ahead. What do you suggest? I'm ready for both.
So stop here.
Okay. So we'll do the basic principles of seismic refraction method tomorrow at the same time. Okay?
Okay, sir.
Okay, sir.
Okay, so everything was clear so far? I mean,
Yes, sir.
Yes, sir.
Okay,
Yes,
in
sir.
terms of voice, in terms of slide, in terms of speed, whatever.
Yes, sir.
Okay, very good. So tomorrow when we come, remember, I'm going to start off by asking some questions and finding out whether you understood or not, because Sagar sir has told me most probably you'll get objective type of question paper this time. So if you don't understand, either you are going to score 0 or you're going to score 100. You're not going to score in between. Okay?
Okay, sir.
Yes, sir.
Okay. So who told yesterday, sir? Who was that girl who told me I'll come dressed and you can see me? Who was that?
Mahima, sir.
Ah, so I cannot see anybody now. So because I'm showing this slide. So maybe when sometime when the lockdown is over, then we will see. Okay. So we assemble again tomorrow, and try to read a little bit so that it becomes easy for you to ask questions and easy for you to digest also. Because you have been away from this for a long time. Okay?
Okay.
Yes, sir.
Yes, sir.
Okay.
Sir.
See you
Okay, sir.
and good
Thank you,
night,
sir.
and see
Yes, sir.
you tomorrow.
Bye bye. Take care, sir.
Take care,
Okay,
sir. Be
thanks.
safe,
Bye.
sir.
Bye.
Thank you, sir.
Bye. Bye. Bye.
Thank you, sir.
Bye. Wait into escape. Okay. So now,
Jackass.
is Sagar around? No, Sagar is gone.
Buddy.
Hello. Hello.